This conference will now be recorded.
Okay. Hi, good morning, everyone. Good afternoon. This is our 47th session of TOP bi-weekly project meetings. And we have a special guest for today, as always. But before we get there, a couple of announcements and updates about our work at TAP. So first and foremost, tomorrow is a big day for TAP. It's the Tech Day. The OCP have been having tech days all through May, and the last event is the TAP event. It's a 3-hour, very condensed half day full of sessions by our community members, and it's tomorrow. So the ask here from everyone is to register and join. We plan to cover a lot of interesting sessions about where TAP is going and what TAP has been up to, in case you've missed the rounds and the work streams and you were not able to follow them all. And also by sessions by our contributors, Intel, NVIDIA, Meta, Calnex, TimeBeat, Trimble, Raken, on different developments, whether they're in the hardware or in the software, and in general about the democratization of time, precision in data centers. Every session is going to be a blitz of 20 minutes and will be packed with information. Our team will also have the ability to chat with you along the day. And so we look at it as a networking opportunity, collaboration opportunity, and we encourage you all to join us for that day. Does anyone have any questions or comments about the Tech Day tomorrow? That's great. Another announcement is coming from the API workstream. That's workstream number 3, one of the very first workstream we ever announced. It is led by Georgi from NVIDIA, and it has reached a draft proposal that covers top APIs. We focus on the API for time-aware applications, not the implementation that much. And the draft is open for reviews. The information about the draft was shared with the workstream mail group. If you guys think or want to be part of it, what I suggest is that you go into our wiki website and get in touch with Georgi, and we'll get you up and running with the email list and the review permissions. Let's see if anyone has any questions or comment about that. I think it's a very important milestone that we reached recently, and I wanted to make everyone aware of that. Awesome. And that concludes the announcements. And Ahmed, would you like to take the lead on number 3?
Sure. Thank you very much, Elad. And also, just to clarify, so the Tech Day is free, so please register. So and hopefully we see you tomorrow. So it's a pleasure to introduce today's speaker. Nir Laufer has over 18 years of experience in developing synchronization and timing products. As ADVA's VP of products, Nir is responsible for development of Oscilloqartz next generation timing, delivery, and assurance products lines, as well as Cesium atomic clocks. Nir also represents ADVA and Oscilloqartz in ITU-T SG15 Q.13 and contributes to the synchronization standard development. So today's talk is about ADVA's advanced TimeCard and SyncModule for data center synchronization. So it's been about 2 years now that we announced basically the TimeCard and so on. It's been great to see the industry basically adopting to this form factor where you can use an x86 as I like to always use this space analogies as a rocket ship, and then let the time to be like a payload that you can just add on PTP or any other things, like can be like, again, you can have based on application NTP, or you can go all the way white rabbit, but the time, the accuracy gets provided by the time card. So with no further ado, Nir, the floor is yours.
Thank you.
Nir, you're now the presenter and you can push the screen share.
Okay. Can you see my screen now?
Yes, we can.
Okay, thank you. So first of all, thank you, Ahmed, for the introduction. I'm very excited to be here, and thank you for the invite. As said earlier, TAP was very active in contributing to the development of TimeCard. And in today's session, I would like to give you some insight to the version of the TimeCard we've developed in Oscilloqartz. So we'll start by introducing the card and the sync module, which is the heart of this card. I will also talk about some of the challenges that we've encountered throughout the years when trying to use GNSS, starting from the antenna installation through the use of GNSS ongoingly. And we will try to explain which features we've added into the TimeCard capabilities that's supposed to address these challenges. We will also talk about sync jack, sync probing and assurance, as well as jamming and spoofing detection. And eventually we'll talk about holdover challenges. So with no further ado, let's start with a short introduction to the 5400 TimeCard. Since I assume most of you are quite familiar with the TAP TimeCard, I would try to focus on the differences or the features that we've added on top of the TAP TimeCard functionality. So again, the basic functionality of the TAP TimeCard are supported. And on top of that, there are additional features that we've included, and I will try to focus on these primarily. So starting from the TimeCard itself, I think one of the key features that is included in the card is that it has its own PTP capabilities, both as a grandmaster and as a slave. It is important to emphasize that the PTP stack is located on the card itself, so it's not PTP packets or a stack that is implemented on the x86 server. In this example, it's located on the card itself. It can support up to 64 unicast clients at the full packet rate. It can support, as you will see later, multiple PTP profiles, and can also do a profile conversion. On the card itself, there is a GNSS receiver. It is currently an L1 receiver, but we are now working on L1 and L5 version, which would be a multi-band variant coming soon. There is also NTP server capabilities, again, native to the card itself. And in order to have a resiliency, we are supporting a PTP input to the card through the Ethernet interfaces that are part of the TimeCard. That allows us to create a backup to GNSS. On top of that, there are sync probing and sync monitoring capabilities. We call them sync jack, and I will try to elaborate on these capabilities today. The use of GNSS can be done in different ways, but in all of these cases, there is a need to assure the timing coming from GNSS. So I will talk about that later, and the use of different oscillators. So these are all key features of the TimeCard. In terms of the use, it's very similar to the TAP TimeCard. It can be fitted into any PCIe slot. Power is taken from the hosting device. There is a PCIe connectivity to the x86 server. But on the TimeCard itself, as mentioned earlier, there are different building blocks, including all the PTP functionality, master, slave, boundary clock, NTP server, the PTP probe, as well as the different variants of the GNSS receiver, the oscillator. And then there are different physical interfaces that are available to either receive timing or generate and provide timing. These are the PPS and time of day, clock, multiple Ethernet ports, as we will see later. So let's have a closer look into the TimeCard. On the right, you could see the PCB and the high-level overview of the card. In red, I've highlighted the 5400 sync module. The sync module is the heart of the time card. It includes all the key functionalities. On the time card itself, there is the physical connectivity to the different interfaces and the oscillator that provides the holdover stability. Looking at the left, you can see the faceplate of the time card starting from the GNSS antenna input. As you will see later, the use of a standard GNSS antenna is optional. There is an additional option to connect to an external smart antenna. This is done over the copper or fiber ports. Over the copper or fiber ports, we can also provide the PTP and NTP services. The copper port is also capable of providing power over Ethernet that is powering the subtended device, in this case, the smart antenna that can be used instead of the integrated GNSS receiver. And below the time of day and PPS, there are two IOs that are used for PPS and clock. It could be either input or output, depending on the application. It can either be used to provide timing to, for example, a NIC, or can be used as an input to either provide an additional reference to the time card or to monitor the signal under test when the time card is used for monitoring. And at the bottom, there is a 1 gig fiber port, again, capable of providing the PTP and NTP services directly from the card. I mentioned the sync module, which is the heart of the card. And so in here, you could see the sync module form factor. We are also offering it as a standalone product. It is 22 by 42 M.2 card. And all the key functionalities that I mentioned earlier are basically implemented on the sync module itself. And again, the capabilities are part of the sync module, and it can be replaced if there is a need for different, for example, GNSS receiver or different interface technology. Then the sync module can be replaced. It is hot swappable and part of the time card design. We are offering a number of variants of the time card. These are mainly corresponding to different oscillator types, starting from the basic Stratum 3E 060, what we call a quartz, then going through the quartz HQ+, that's a very high-end 060 that provide an extended holdover, through the HQ++, that's a double oven 060. We will see some results of the double oven 060, and then eventually the rubidium. When the HQ plus or the rubidium are used, we are using a double width card, and there are 4 SMA connectors that can be used for clock and 1 pulse per second. But the rest of the functionality is identical between the cards. So I mentioned earlier that one of the key enhancements to the time card is the use of PTP interfaces directly from the time card. So the question that might come to mind is, why do we need direct connectivity or PTP connectivity from the time card? So there are different use cases that I will review today that can be supported when there is a direct PTP connectivity between the time card and the subtended device. I hear a bit of echo. I'm not sure if you're all on mute. Thank you. So we will see a few use cases. The first one is when we want to connect. I still hear the echo. Okay. So the first use case is when we are using a smart antenna. The smart antenna is connected over Ethernet interface that provides a local connectivity between the smart antenna and the time card, and this is done using PTP. Another use case for a direct connectivity from the time card is the use of the time card in ORAN application where the PTP grandmaster is connected to the frontal network, and we will review this use case as well. Another important use case is the use of PTP as a local interface to carry time and frequency. Instead of using 1 pulse per second and time of day, we can use a PTP that provides all this information in a standard interface, but it has its own advantages. It includes all the metadata that is needed, such as leap second and others. It also compensates for the cable delay since it's a two-way time transfer. So the use of a PTP is ideal when we want to interface with other subtended devices. And the last important use case is when we want to use a time card as a probe, as either a PTP probe or a sync probe. We would need to connect the device under test directly into the time card in order to avoid any inaccuracies coming from the indirect connectivity. And in this case, we will use the onboard Ethernet interfaces. So these are some of the use cases that we will review today that shows why Ethernet connectivity is needed on the time card. In terms of the capabilities of the time card, it is primarily designed for enterprise applications, data center applications, and telecom applications such as ORAN, but we are not limiting the scope to these applications. We are supporting different PTP profiles, such as a power profile, the broadcast profile. So in the future, the use cases can be extended to these applications. Going to the details of the exact PTP profiles that are supported. As a master or a slave, you can see on the left all the telecom profiles. G8275.1 and G8275.2 are the main profiles that are being used for 5G applications. The enterprise profile, PTP over IP, and in the middle, power utility profiles that can be still served from the time card, and on the right, the broadcast and automotive PTP profiles that are supported as well. So let's take one example for the use of the time card in the open radio access network. In this case, we are specifically reviewing the ORAN application, where we have the split between the CU and the DU, and eventually there is a frontal network connecting the DU to the different ORUs. And in the ORAN specification, there are a number of architectures to how the different elements within this architecture can be synchronized. At the lower layer split C3 configuration specifically, in this example, the synchronization architecture is starting from a PTP grandmaster, which is located in the frontal network, and it is providing timing to both DU and to the radio units. So timing is flowing from this grandmaster on both directions. This is typically done using G8275.1. So one of the options to do that with a time card that supports PTP interfaces directly from the card is shown here. Typically, the frontal network is connected through a boundary clock. This is typically a switch that includes the boundary clock capabilities. The time card in this case would be fitted into the DU, but in order not to degrade the accuracy, timing can be provided from the time card through the PTP interface into the frontal switch, and the frontal switch as a boundary clock would then propagate the time to both DU and to the radio unit. Since the time stamping in the time card is done on the physical interface very close to the physical layer, the accuracy that can be provided in this type of architecture is extremely high. So looking at, again, the overview of the PTP features, fully featured PTP grandmaster boundary clock and slave. We're also supporting APTS. It stands for Assisted Partial Timing Support. This is typically the use of a PTP input, which is used as a backup to GNSS. While GNSS is available, the PTP input can be calibrated. And so this is an option that is supported by the time card. There is also a conversion between different PTP profiles. This is mainly used when is also used as a boundary clock. So there could be a case where there is one PTP profile coming in and another PTP profile coming out. For example, G8275.2 IP over PTP over IP is coming into the time card, and then it is generating its output G8275.1, which is Ethernet multicast. So these type of conversions are supported. There is an option to compensate for the asymmetry. This can be done either dynamically if GNSS is available or manually. The PTP packet generation, as mentioned earlier, is not done by the x86 server. It is done by the FPGA located on the time card, and therefore it's a hardware-based implementation, and that helps in denial of service attacks. And PTP can be either untagged or tagged with VLANs. I also mentioned that there is an NTP server capabilities on the time card that can be served. Again, this is not an NTP daemon running on the server. This is a dedicated NTP server implemented in the FPGA. It is using hardware-based timestamping, so the accuracy of the NTP timestamping is very similar to the accuracy of the PTP timestamping, typically within 100 nanoseconds from UTC. And the number of transactions per second that can be supported is 500,000 transactions per second. Since it is not served by a CPU, but by a hardware logic, there is basically a hardware logic in the FPGAs that automatically responds to any NTP request coming through one of the Ethernet ports. So this is, again, for applications who still uses NTP. This could also be served from the time card. So first challenge that we've came across when using GPS or GNSS was the installation of the GNSS antenna. Most of our products today, and also the time card from TAP, is using an integrated GNSS receiver, and there is an external RF cable that should be used to connect the external antenna to the receiver. While this seems simple, installing an RF cable can be challenging. First of all, the cable itself is quite expensive. It's very thick cable, so it's hard to maneuver the cable inside the building. The cable delay itself must be compensated in the receiver, and sometimes the exact cable length is unknown. For example, you might take a subcontractor that would install the cable, and he might cut 10 meters of cable without letting you know, and you assume that the cable is in a certain length, but in reality, it is 10 meters shorter, and this could result with close to 40 nanoseconds of an error. So the cable compensation is needed and sometimes tricky. When using an RF cable, the distance between the GNSS receiver and the antenna is limited. Typically, it's in the range of 150 meters. There are options, for example, to translate the RF into fiber and transmit the RF signal over fiber. We've seen a few examples for such a solutions in TAP in previous talks. And this could be used to extend the reach, but this is relatively expensive solution. And eventually the installation of the RF cable is complicated and requires some expertise. And so all these challenges are challenges that we are quite familiar with. And again, these are challenges that we are facing when we're using the standard architecture where an external antenna is connected over an RF cable. So what we are offering as an option in the time card is to not use the RF cable to connect to the receiver, but instead use an external GNSS smart antenna. And instead of connecting an RF cable, we are using PTP to send the time between the antenna and the time card. So on the left, you could see an example for a standard time card. Again, this is, I would say, a typical architecture where a GNSS antenna is used along with the coax cable. This is an option that we are supporting on our time card, and it's also supported on the TAP time card, but we believe that there are additional options that providing significant improvements when we're using a smart antenna. And on the right here, you could see the smart antenna. The smart antenna itself includes a GNSS receiver, but the GNSS receiver is automatically connected inside the smart antenna to a logic that translates the time recovered from the GNSS receiver into PTP packets. So there is no long RF cable involved. The timing is immediately converted into PTP and then sent over either copper or fiber to the subtended time card. The time card itself is recovering the time from PTP and then generating for example, 1 pulse per second that can be connected to the NIC card. So again, it is important to emphasize that the PTP in this case, it's just a local connectivity. There is no use of the PTP outside of the card. It's just a very straightforward way of providing the time from the smart antenna into the subtended card. Looking at the typical TAP application, where we want to eventually provide 1 pulse per second and potentially a clock to a subtended NIC, we will use the 5405 outdoor smart antenna. We will connect fiber or copper and to the time card. The time card again would be a PTP slave that would locally recover time from the smart antenna. We are typically using a G8275.1 PTP profile because it's the easiest profile. It requires almost no configuration. It's the most plug and play PTP profile, and it sends and receives 16 packets per second. The time card is then recovering the clock locally and then provide a pulse that is provided into the NIC. So from the NIC perspective, the interface is similar. It just happened to be that the GNSS receiver is located on the external antenna and not on the time card itself. Here you could see a few examples for the 5405 outdoor. And again, it's a IP66 hardened, suitable for extreme conditions. There are different variants of the 5405 smart antenna. We are offering it in a single band mode, a dual band L1 and L2, and a dual band L1 and L5. This is another advantage of using an external smart antenna, since you could, going back to the previous slide, you can decide which type of smart antenna you want to use, whether it would be single band if you want to optimize cost, or multi-band, and if it is a multi-band, which type of multi-band bands should be used, depending on the application, the requirements, and the expected cost. So we are basically separating the GNSS receiver from the time card and using a standard PTP interface to provide the timing to the time card. Next challenge that we were facing. Yes, please.
Before we jump to the next challenge, there are a couple of questions from our team here. Can we?
Sure.
Sure. All right. Let's start with not with Ahmed. Ahmed, you'll get to go next. The first question we got, other than Ahmed's, was from Son. Son, would you like to ask a question? I will read out the question. Other than drawing power, does the card interact with its host platform via the PCI bus interface?
It's a good question. So there are two options. You could either just use power from the hosting machine. In this case, it would basically be a power sucking element in the host. But you could also create a management interface between the card and the host. And then we are supporting the standard drivers, as Linux would identify the PHC that is available on the time card. So from the host, it could be used as similar to the TAP time card, to provide PHC to CIS, providing TS to PHC, and all the standard Linux function can be supported. You could also configure the device through the PCIe. You could either open an Ethernet connectivity. We have an Ethernet over to PCIe bridge that allows us to create a direct connectivity, Ethernet connectivity between the card and the hosting device. So there are different options to do that. The most basic one is just to provide power, but if in additional capabilities such as Linux timing capabilities are needed, or whether you want to manage the card through the PCIe, these are also supported. I hope it answers the question. I see a question whether it supports Windows. So again, if we're talking about a power sucking element, yes, you could install it in any server that provides power to the card, but in this case, you will obviously not be able to use the standard Linux functions. But once you're providing power to the card, then you could use the external Ethernet interfaces to connect to the device, to configure it, and basically it would be the PTP Grandmaster that I mentioned earlier, which happens to take power from a Windows hosting machine.
Just elaborating on that, like for the Windows, is it possible, or I mean, do we have that, like, let's say, to expose the PHC or anything like that?
Currently, it's not something that we've done so far, but if there is a simple way of doing that and it's needed, it's something that we can definitely consider.
Yeah, sure. So there are a handful of questions. Do you want me to go through them now, and then we continue on the presentation? You want to have it in the end?
I will try to answer them at the end, if that's okay, because I'm afraid that if we don't have sufficient time, I will not be able to show. But at the end, we will try to keep a few minutes for questions and answers. And if there are additional questions, you are always welcome to contact me. I have my email at the end of the presentation.
Absolutely.
But thank you for all the questions. Okay, so the next challenge that we came across was related to GNSS assurance. As you probably know, GNSS is extremely good technology, provides amazing accuracy, and it's all for free. So in terms of the technology, it's mature and available, but there are a lot of vulnerabilities and threats that are coming along with the use of GNSS. Some of them are intentional, such as jamming and spoofing. Some of them are unintentional, such as adjacent band transmitters, or even equipment failure that could affect the availability of GNSS. So when we are using GNSS, we always have to take into account the cases where GNSS might not be available. And this is a well-known problem, and there are a few actions taken by different governments trying to address the problem. I think the most important one is taken by the US government. There was an executive order issued in February 2020, and it asked for users of GNSS to, first of all, protect their GNSS use, to be able to define, first of all, what type of critical infrastructure should be protected. They have listed a few critical infrastructures: power grids, finance, transportation, communication, and data centers. And so these are critical infrastructures. I just try to think to myself what would happen if my daughter would not be able to browse to Instagram. This would definitely be a problem. So this is a critical infrastructure. We have to protect our data centers. And in order to help users protect their GNSS installations, the Department of Homeland Security have issued a conformance framework. There are additional activities that are being taken in the US, such as NIST working on another framework, and IEEE is working today on a draft of a resilient PNT guidelines. So there is quite a lot of work being done. I think the most useful guideline and framework today is still coming from DHS. And in the following slide, you could see the framework coming from DHS, Department of Homeland Security. It basically divides the PNT, the positioning, navigation, and timing devices, into different levels of resiliency, and each user can select the level that he is interested at based on the risk tolerance, the budget, and the application. Looking specifically on the different levels on the right, you could see that they are differing from one another by different building blocks, mainly the number of PNT sources. For example, GNSS is a PNT source, a PTP could be a PNT source. So, for example, a level 1 system would have only one PNT source, and level 3 would have multiple PNT sources. Another key aspect is the verification of these sources. So we cannot blindly assume that we can use these sources. We need to verify them. And the question which comes to mind is how exactly we are verifying GNSS. This is specifically interesting when we are talking about spoofing attacks that tries to basically fake an authentic signal, and it makes the verification even harder. So this is just a framework that we could keep in mind while trying to talk about the TimeCard and the fact that the TimeCard would provide timing into critical infrastructure such as data centers. So looking at the way that we are proposing to protect such an infrastructure, we are offering a multi-layer protection. The first thing that we could do is to use special antennas. These are anti-jamming and anti-spoofing antennas. One example is an antenna that basically reduces the gain of signals coming from low elevation while increasing the gain of the RF signal coming from high elevation, assuming that most of the attacks would be coming from the ground. So for such an attacks, we can to some extent limit or reduce the exposure by using these directional antennas. Second layer of protection is done by the GNSS receiver itself. Again, there are different types of GNSS receivers in the market. Some of them are more advanced than the others. And we will see later that there are different types of, for example, spoofing attacks, and some of them are not capable of detecting all types of attacks. For example, if there are sophisticated attacks, then at least from our experience, many of the commercial timing GNSS receivers are not capable of detecting these attacks. So in order to provide an additional level of protection, we have developed an algorithm that is sitting at the output of the GNSS receiver, basically monitoring the data collected by the receiver, and based on, again, advanced spoofing detection mechanisms, we are able to detect some of the more complicated spoofing attacks that were not detected by the receiver itself. The third layer is related to the SyncJack. The SyncJack is the GNSS monitoring capability that we can do against other signals that are available. For example, if we have a GNSS receiver and a PTP input coming from one of the Ethernet ports on the card, we can potentially compare the timing coming from each one against the other. We are assuming that they are coherent to one another. And if we are seeing that there is a deviation between them, we are able to detect that the GNSS, for example, or the PTP is spoofed. And in this case, we will at least alert the user that there is a discrepancy between timing recovered from GNSS versus the timing recovered from PTP. And the last layer is the network layer. All these devices are connected to a centralized network management system. And on the network management system, we're able to provide another level of monitoring. And we're also using machine learning to identify different type of jamming and spoofing attacks. We will see an example later. So basically, the protection is done in 4 different layers that's supposed to protect us from the different GNSS threats. I mentioned the spoofing as one of the most complicated attacks. And the reason why it's complicated is that there are different types of spoofing. Some of them are what we call asynchronous attacks. These can typically be done with the low budget equipment, such as software-defined radio. And basically, in most cases, it's a hard takeover, meaning that there's a device that is spoofing their antenna would send time and location, or one of them that is far from the truth, and it would also do that with the high power in order to brute force kidnap the receiver. And so this is asynchronous attack. This is an attack that is easier to detect because, again, there is a big change in location, time, or power while the attack is generated. A more complicated spoofing attack is the synchronous attack. This is harder to do to create. Typically require high-end simulators, for example, and it is doing the attack very smoothly, starting from a signal, RF signal, which is identical to the genuine GNSS signal. So it sends at the beginning the right time, location, almanac, so all the data look legit, and then slowly increases the power to hijack the receiver. And again, this is something that is harder to detect since there is no clear changes that are observed. And again, some of the commercial timing receivers are capable of detecting asynchronous attacks, but synchronous attacks are harder to detect, and we have not seen a lot of commercial receivers that are capable of detecting the synchronous attacks. So in order to try to overcome this problem, we've added another layer of protection. On the GNSS receiver outputs, we are collecting all the data coming from the receiver, and then we are running our own algorithm to detect these advanced spoofing. It is a stateless detection, meaning that we could even run in an environment which is already spoofed. We don't need to operate in an environment which is not spoofed in order to detect the spoofing. It can detect positioning discrepancies, time discrepancies, multi-constellation, multi-band spoofing. Some of the attacks are starting with jamming of certain band and then spoofing the other band. So these type of attacks can be identified as well. And eventually, once the attack is identified, alarm is then generated by the system, and the user has the option to decide whether he wants to disqualify the GNSS in case this attack is generated, or whether he just wants to be informed. If he decides to disqualify the reference, then we can fall back to alternative time sources such as PTP, or to fall back to Holdover, where we are basically counting on the TimeCard oscillator. I mentioned earlier the DHS resiliency levels, the 4 levels, and since the TimeCard is used in data centers, and these are, as mentioned earlier, classified as critical infrastructure, we believe that our target is to achieve a resiliency level 4 in the TimeCard, and this can be done by using multiple synchronization inputs directly to the TimeCard, such as GNSS, Sync, and PTP, and be able to properly detect the attacks. So we will be able to switch to the alternative backup or to holdover when the attack is generated. Yes, please.
You have more questions. Let me know when I can chime in.
Okay. I think we will keep at least 10 minutes for questions. So I will review the following section, and then we can stop for questions if that's okay.
Or I will suggest you continue the presentation, because we can have it recorded. I really don't want to miss all this amazing information you have in the presentation.
Okay, let's do that.
Okay, so if you remember earlier, I mentioned the different layers, and the most upper layer is the network management layer. So the first 3 layers are done on the receiver itself, either the antenna, the receiver, or the device. But eventually, we believe that the strongest layer is the network layer. And what we've developed, and this is information that I already presented in TAP previously. If you want the full presentation, you can probably go through the session itself and go through the different details described there. But basically, we are collecting data from the receiver. This is typically done through SNMP, and all this data is then analyzed by the server. We are running machine learning algorithms to detect anomalies on each of the receivers. And once anomaly is detected, we can then generate a command into the receiver telling him to stop count on his GNSS receiver and to switch to either holdover or alternative backup. So this is a type of GNSS firewall capabilities that we are supporting. Again, this is coming from the network management layer as part of the GNSS assurance capabilities. What type of information are we collecting from the receiver? We are typically using quite standard information such as latitude, longitude, and altitude, and the table of GNSS satellites observed with carrier to noise, azimuth, and elevation. So this is the most basic information. There are additional capabilities that we can support if the receiver is capable of providing an additional information such as automatic gain control. This is a nice video that I presented in the past. It shows what exactly can we generate once we've collected this basic data. So since we know which satellites are observed and where they were observed and what was the carrier to noise, we can overlay this data to create what we call the heat map. A heat map tells us from which direction we are capable of seeing the signal with the required strength and quality, and from which directions we are not able to see the signal with the right quality. In this example, a GNSS antenna was installed close to a telecom tower, and you could see that from this direction, it's a bit hard to see here, but you could see these blue dots here, that's showing that the signal coming from this direction was not as good as signal coming from other directions. And if you look at these simulations here, MATLAB simulations, you could see that, again, you could see this shadow, if you wish, of the reception of the signal over the antenna. So this is the type of information that we can collect. And this is, first of all, observed to the user from the network management system. So we can drill down to a given site, look at the usage heat map and the carrier to noise heat map. This would tell him whether the antenna is installed correctly, whether there are some directions, for example, from which he cannot receive the signal properly. This will allow him to optimize the GNSS antenna installation. We're also providing some health tests that would tell him whether the site is a bad site or a failed site or a pass sites based on the criteria that the user can configure. For example, he could decide that he wants to have at least 5 satellites available with a certain carrier to noise throughout the test. And if that's not the case, then we will consider this site as a failed test. So that's a bad site, a good site. And again, there are criteria that can be configured. But this is something that the user can drill down to and look at. This is not something that you could do when you have hundreds or even thousands of receivers in your network. So on top of these drill down capabilities, we've also implemented in the background the GNSS assurance firewall. This is a mechanism that scan all the GNSS receivers, and based on the data collected, identify automatically the sites where there is obstruction to the GNSS signal, whether there is spoofing or jamming, and these would be then generated as alarms that would be visible to the user. So out of the, for example, 1,000 sites with GNSS receiver, he will get notification only for the problematic sites where a problem were identified by the machine learning algorithm, and then you would drill down to these sites and will try to troubleshoot. As mentioned earlier, on top of just reporting the potential problem, we are also capable of instructing the receiver to stop using GNSS in case one of these alarms is generated. The user is capable of deciding which alarms would trigger this command, but once alarms are generated and the user configures this rule, the device would be notified and will stop using GNSS until it is instructed otherwise. I think we are running a bit out of time, but I would go through there are 2 additional problems that we identified. The second one is related to sync assurance. The sync assurance is basically the ability to know whether timing is accurate in your network. We are making a lot of assumptions when designing a network. For example, that there is a certain amount of packet delay variation, of asymmetry, and that the packets are arriving on time, that the timestamping done by the different elements is accurate and reliable. And all these assumptions are valid assumptions, but we have to validate, at least in certain points in our networks, that these assumptions are met. And for this, we have developed the in-service sync assurance. If we want to typically monitor the quality of timing in our network, we will typically need a test equipment, which is typically too expensive for in-service installation. We cannot keep it installed ongoingly and just keep it there. So the ability of our, for example, technicians or network operators to monitor time ongoingly is limited if we're just assuming that they will count on test equipment. So in order to overcome this problem, we've added testing capabilities into the TimeCard. Basically, we are having a tester, a PTP and a Sync tester included in the device. You will see later the capabilities of the tester, but it is capable of measuring physical signals, sync signals, one against the other, and compute the time error or the time interval error between them. The raw data is then sent into an FTP server, where data is then collected by the network management system, concatenated, and then certain analysis can be done on the data, such as time error, time interval error computation and display, TDEV computation, and M-type. So there are different type of metrics that you can compute on the measured data. As mentioned earlier, within the TimeCard, there is an FPGA. In the FPGA, we've implemented time error counters. These are hardware counters that are using nanosecond accuracy. We are able to monitor physical signals one against the other. For example, GNSS versus PTP recovered signals. Each of them is, for example, providing a 1 pulse per second. We can then monitor the difference between these two pulses in nanosecond granularity, and this raw data is then saved and sent, as mentioned earlier, to the server. On top of the physical signal monitoring, we are also providing timestamping monitoring, so we can monitor timestamping coming from a subtended device connected to our TimeCard versus the timestampings that we are creating ourselves when the packet arrives using a reference, using a GNSS. So we basically use the timestamping to compare the two clocks, and we'll see an example later. All this data, again, is collected from the TimeCards to the different from the different locations into the centralized network management system. It's the same network management system that I mentioned earlier used for the GNSS assurance. And again, this data is then aggregated and eventually analyzed. A few examples or a few use cases for the sync jack capabilities. Let's assume that we have a boundary clock in our data center, and we want to make sure that this boundary clock is properly sending timing to the subtended devices. What we could do is to connect the TimeCard as a probe. The TimeCard in this case is acting as a slave. It acts as a slave just to interrogate the boundary clock to send the PTP packets to him. Then towards the sync key and the PTP timestamping coming from the sync and delay request message, and compares them to the timestampings that we are using when the packet arrives to the TimeCard. These two are then compared one against the other, and on the right you could see the time error is then displayed in the network management system, and MTA in this case can be computed. So that's an example for how we are using the Ethernet connectivity on the TimeCard to monitor a boundary clock in this case. There are cases where there is no PTP connectivity between the device under test, but it is capable of providing a physical layer signal. This could be a 1 pulse per second, the clock, or a 2 megahertz signal. In this case, we are using a physical layer connectivity. This could be, for example, a 1 pulse per second or a clock that would be connected to one of the coax connectors on the time card. And again, we are doing the same measurement, measuring the time error between the signal under test and our reference, and the raw data of the measurement event sent to the network management system for further analysis. The last example is when we are using the time card to monitor the network itself. Since both Grandmaster and time card can be connected to GNSS, they have a common reference, then we can use the PTP packets exchanged over the network. This could be, for example, a PTP unaware network to quantify the asymmetry and the packet delay variation of the network. So we are able to display the asymmetry. There are specific metrics related to asymmetry, such as a two-way packet selection that are defined by ITU-T, and we are able to display all these related metrics that would allow us to understand whether the networks, the PTP network, can be used to deliver required accuracy. The last piece of the challenges that we were encountered related to oscillator selection and the holdover. I used to call it the good, the bad, and the ugly. Sometimes it's very hard to say who's the good, who's the bad, who's the ugly. It is true that when using GNSS, when there is a GNSS failure, it could be quite ugly. It could be, again, jamming, antenna breakdown, the lightning, cable cut, equipment failure. On the right-hand side, you could see an example coming from the Ukraine war. There were quite a lot of GPS jamming events reported in the border between Russia and Ukraine. So this by itself could result with a failure that could last for a long duration of time. So when we are considering the oscillators that we are going to use on a time card, we have to consider this long-term holdover. We need to consider a long duration. This is typically few hours to a few days, where we would have to operate the Grandmaster within the time error expectations, as long as there are no other timing interfaces or references available. So if we are using GPS and oscillator and we are losing the GPS, we are counting on our oscillator to provide the time or to hold the time. So one of the challenges that we were facing was that when there is a big impact on the holdover specifications or capabilities coming from temperature effect on the oscillator. And this example is taken from a base station. You can see some base stations are installed in the desert. Some of them are installed in Arctic areas, and there is a big difference in the temperature that is would be exposed to. But I think the similar problem is relevant for data centers. There are data centers who are well controlled, but there could be, first of all, failures, and there are also data centers who are maybe less controlled in terms of temperature. So we have to take the temperature effects into account. When looking at the different type of oscillators, I like to show them in two verticals. First of all, the temperature stability and the aging per day. So looking at the rubidium holdover, we can see that it has a very good aging per day, probably the best for this form factor, but temperature stability is not as good as a super DO60. DO60 stands for a super double oven controlled oscillator. So we're using two ovens to isolate the quartz from the surrounding temperature. Such an oscillator is having a 5 times better temperature stability versus rubidium. But as you can see here, the aging is not as good as the rubidium. What we could do in order to compensate for the aging is to learn the aging patterns while GNSS is available before the holdover period starts, and then compensate or extrapolate the behavior while GNSS is not available. By doing so, we are able to improve the daily aging or the residual daily aging of the oscillator. And eventually that's help us to improve the holdover capabilities. But again, in terms of temperature stability, the double oven oscillators are better. In terms of daily aging, the rubidiums are better. And the question of whether to use one or another is really a question of the application. I will skip some of the slides. This is a table showing the specifications. You can see the details here. Again, temperature stability of the rubidiums are not as good as a double oven oscillator, but the aging is better. And eventually, we've run a test in the chamber trying to compare the two, trying to see which one would behave better when we are applying some temperature profile. So we used a rubidium and a super double oven 060 in the same oven, and we run a certain temperature profile trying to change the temperature by 10 degrees. So it was not a huge temperature change, something that I think could happen even in data center environment. And when we looked at the steady state results, when GPS was available, we could see that there is some degradation when we are applying the temperature changes. On the bottom here, you could see the temperature profiles. We could see that there are some changes, but it was not extreme. But when we disconnected GPS, and then the clock could not steer itself back to GPS, then we could see a big impact on the holdover when we were running these temperature cycles, while the double oven 060 was not affected by these temperature cycles since it is well isolated in terms of temperature. So this is just an example to show that there are, in a nutshell, there are no good or bad oscillators. It's just finding the best fit to the application, and that's why we've chosen to offer different oscillator types. Some of them might be more suitable for a temperature controlled environment, and some of them might be more suitable for a more harsh environment where there could be a wider temperature variations. And with that, I will conclude. I will just mention the main enhancements that we've tried to add into our TimeCard: PTP and NTP directly from the card, simplify GNSS antenna installation as an option by using a smart antenna, advanced jamming and spoofing detection, the GNSS assurance, sync monitoring and assurance with the sync check, and the multiple oscillator and holdover options. So with that, I would like again to thank you for inviting me, and I'm not sure if we have time for questions, but I can stay here if there are more questions, or again, I'm happy to take any questions offline. Thank you.
Wonderful. So let's open the floor for questions. Anyone, again, thank you for staying this long. Anyone wants to start with the questions before I go through whatever we have in the chat? Maybe we need icebreakers first, so I'll go with a bunch of questions.
Okay.
So the first one is like when you mentioned the profile, did you have a chance to look at the DC PTP profile, basically the profile that Michelle and the community here developed? Like any concern there or something, because there were, let's say, some special things there.
Yes. So we have looked at the data center profile, and this is something that we are planning as part of the product roadmap. Obviously, we will need some feedback from the industry whether this is a profile that would be used by the clients. But this is something that we can definitely develop. Again, the product itself already using IP unicast and Ethernet, so both layers are supported, and tweaking it towards one of the profiles is not a big effort. But again, we want to first see whether this profile is well adopted and in use, and then we will be able to add it as a software upgrade to the TimeCard.
Wonderful. So the second question is, did you guys have any chance to test this, like the TimeCard, let's say in hyperscale with maximum number of clients in unicast? So
again, when using IP unicast, the scale of the card is up to 128. Up to 64 clients at the full packet rate. So the intention of this card is not to provide timing to all the clients in the data center, right? That's not the intention. If there are hundreds of thousands or even thousands of clients in the data center, this will not be done through the TimeCard. The PTP interfaces are, as shown earlier, are designed to interconnect to an external antenna, or to be able to do monitoring, or to use 75.1 connected to the boundary clock on the frontal. These are the use cases. But to your question, it is not designed to support hyperscale data center synchronization directly from the card. In this case, we will use a standard TAP architecture where ports would be connected from the TimeCard to the NIC, and the PTP stack that serves the clients would be implemented on the host.
Yeah, the Ethernet jacks were just like, I just wanted to like basically confirm that, which you confirmed. So basically, it will, again, similar to the TimeCard, it will provide the payload, and then you have like the rocket ship, basically a PTP, doing the dissemination across the network.
Correct, yes.
And then I think you already answered the third question, which was like, what does it show on the PCIe bus? Like if we want, let's say, the like POSIX clock, which you said you confirmed it can. The
Yes.
other one is what's the precision accuracy penalty that we'll get like when we use a smart antenna versus connecting directly the antenna to the GNSS? That is, I mean, it's probably like the precision or whatever you're gonna get through that PTP connection, right, from the smart antenna to the TimeCard, right?
Exactly. It's like the accuracy of one boundary clock, if you wish, because you have two PTP ports. Since we are using hardware timestamping on both sides, from our experiences, degradation in accuracy is typically less than 10 nanoseconds. Again, it is important to emphasize that when you're using a GNSS RF antenna, you're also losing a lot on the accuracy. You just don't know exactly how much you are losing, because you have to compensate for the antenna itself, for the cable, and there are a lot of uncertainties there. So although you don't immediately know what is inaccuracy, you are losing accuracy on a standard RF antenna installation. And we believe that this architecture, when using PTP, is actually providing a higher accuracy versus using an RF antenna.
And I think you answered already the fifth question right now, which is basically what's the protocol between the TimeCard and the smart antenna? I guess it's just a standard PTP over at 100 gig or 1 gig. So sorry, 100 meg or 1 gig connection. Is that right?
Correct. And you could use different PTP profiles, but the profile of choice is typically G8275.1, because it's, again, slow protocol, 16 packets per second, and using Ethernet multicast. So it's basically plug and play. You don't need to configure IP addresses or packet rates. It's just plugging the antenna, and it starts sending these 16 packets per second, which the TimeCard terminates and recover the clock from. So typically we're using a standard PTP.
Sorry, is that connection a PoE, like from the TimeCard? Does it provide the power to the antenna, or you need a separate power for the antenna?
Yeah, so the Ethernet connection here provides power over Ethernet over the copper, but you could also use fiber connectivity. So you could only power the device from Ethernet, but use the fiber to actually manage and get PTP from. This helps when you want to extend the reach of the antenna. So you could either use an external power over Ethernet injector and still use fiber that would connect to the TimeCard. And we are supporting a single mode and multi-mode fiber. So basically the distance between the smart antenna and the TimeCard is unlimited. It could be even tens of kilometers when using a single mode SFPs.
Yes. And then can you add multiple antennas? Let's say you have an antenna, let's say L1, L5, and one L1, L2, or 3, or whatever. Like, is it possible? Like,
what you could do, since we have two PTP interfaces, you could connect one antenna to each, and then inside it's like a boundary clock. It will run a best master clock algorithm between the two smart antennas. Each of them is considered as a remote master, and it will select one of them. So you could, for example, set a local priority on one, which would be higher than the other, and as long as it is sending clock class 6, it will be selected. And if GPS is not available to one of the antennas, then the other one would take over. But basically, the selection would be done by the TimeCard client.
Beautiful. And I think this, from the picture, you can see there is a auxiliary power connector, which Son basically was asking, which is about the repeated port. Is that right? That's the auxiliary 12-volt connector, right?
Correct. There is, you could power it, the card from three different interfaces. One is the standard PCIe, the other one is this external connector. There is also, if you want to connect the card without plugging it into the host device, then you could do that. I think I even have, yeah, in here you could see an example to how this looks like. You could see the card, and you could just use a standard AC adapter to power the card if you just want to play with it when it sits on your table. So
Beautiful.
this is also an option.
So Venkat, do you want to ask your question? You still here?
Oh, yes, yes. Hey, hi, Nir. The question is about the ORAN S-plane implementation. Could you talk a bit more on what was the kind of work that has been done, or maybe some in terms of the accuracy and performance of the S-plane and the impact of the front haul latency over the PTP?
Yes, so
yeah.
Going back to the ORAN, in the ORAN synchronization architecture, there are basically three options. The first one is when the grandmaster is embedded into the DU. This is not the one shown here, but there are architecture where the grandmaster is embedded into the DU, and then if you want to keep the accuracy at the highest level, you have to make sure that the grandmaster provide timing accurately through the DU. So, for example, if you have two Ethernet ports on different NICs on the DU, you would have to tightly synchronize them in order to make sure that the timing would be provided from the DU into this boundary clock and the frontal switch eventually into the radio units. Another option to try to bypass this problem is shown in the configuration C3, where the PTP is connected directly to the switch, to the frontal switch, and that's what the TimeCard with the PTP interface can support. I'm not sure if it answered your question, but this was the main motivation for the PTP port on the TimeCard.
Would you go back to slide number 12?
Is this on demand?
No, I don't know anything, Herb. I'm not sure.
Okay, okay. So this is typically, you have the radio ORU and the DU and the C3 conflict. So could you talk, if there's any study done if on a front haul packet drops, so how would it impact any kind of drop test? How is the performance of the TimeCard with respect to the accuracy and PTP packet drops?
The packet drops by the switches in the frontal network?
Yes, yes.
Okay, so typically on the frontal, we are using G8275.1, which is a local link protocol. So each of the two peer devices are sending and immediately terminating the PTP packets. So the PTP packets should not go through the switch fabric, and therefore, again, as long as there are no hardware failures, there should be no packet drops in these interfaces. It's also extremely low protocol that could be mapped into the highest quality level if needed. But I'm not familiar with any study that was done on packet drops impact on the time accuracy related to this architecture. But again, I believe that as long as you're using a full on-path support where all the network elements are boundary clocks and using G8275.1, there should be no packet drops, at least not significant ones in this architecture.
Understood. Thanks, Nir.
Perfect. So there's one more question from Dan Geese. I don't think if it's still here. Dan, are you here? Okay, so Dan is asking, has sync jack over IPv6 been added in this clock, or it's still subject to a forthcoming firmware?
So it is still being developed and would be coming in our next release. So it's not yet available on the released version. The released version using IPv4 only, but it is part of our roadmap. So it's being developed.
Wonderful. And I think there was another question from Julian. I don't know if Julian is still here, which was about Julian, you're still here. Can you want to ask your own question about the rubidium clock? I don't know if he's there. So, Nir, can you share more information about the rubidium clock? Like, is it a brand that you guys are using, or like what are the options? Or
yeah, so we are using the 4 oscillators that I mentioned earlier across all our portfolio. So if you would look at our standard chassis-based PTP grandmasters, you would also see the same oscillators. So we have quite a lot of experience with these 4 type of oscillators. Yeah. And again, we have seen advantages and disadvantages in each. And from our experience, the best would be to optimize the oscillator to the customer use case and to the location where the time card will be installed. I have at the background here some examples for holdover that we have taken with the time card, and you could browse through that later, but you could see here a few examples for the holdover. And again, this is not yet optimized, but in the first release of the time card, these are the holdover capabilities. So you could see that, for example, 1.1 microsecond can be held with the D060 for 1.4 days and with rubidium for 2 days. It is important to emphasize that all these values are taken at an almost constant temperature. If the temperature is changing, especially when it's changing significantly, then the rubidium results would not be as good as shown here. And in this case, the super 060, the D060 would have actually better results. So it's really a question of whether there are temperature variations or not. If there are none, then rubidium is definitely a good choice. But if there are some temperature variation expected, then I personally would recommend using the double oven 060.
Interesting. So thank you very much for saying extension. Any more questions before we close the session for today? Calling once, calling twice. Great. Nir, thank you very much. Again, thank you for ADVA for the presentation, and wish a great day for everyone.
Thank you for hosting me, and sorry for keeping you up late. And
oh no, we enjoyed.
Ahmed, one question: would this presentation be posted anywhere?
Absolutely. So this will be recorded, and Nir, please send me the slides as soon as possible, so I'll put it on the wiki.
Sure.
Awesome.
Thank you. Thank you for the invite.
Everyone.
Thank you.
Bye.
Bye-bye.